Hi, Joshua asked me to come up and share something with you. So, one thing that I wanted to do was see what happened if you just looked at three numbers. And I realized that I just wanted them to be different, so I used three different variables. I got here by wondering what would happen if I just had A was smaller than B was smaller than C. And I wanted to see what would happen if could I always get a biggest number somehow. So I just started working with my numbers, and I thought I would pair. Can you see it if I write here? Purple's a little light. Okay, I'll try black, and then perhaps we'll abandon this idea.
I have this board right here.
There's an empty board over here. What's the fun of that?
Yeah. Better? Okay. Yeah. So I have three different ways I compare them. I compare the A and the B. I compare the B and the C. I compare the A and the C. And then after I do this operation, I'm going to have two cards left. I either have the result of A and B paired with C. I just needed some other notation here. I don't know if this is a good one, but this just means I've done my operation on those guys. So absolute values mean other things, sorry. So these are the three things that I wanted to output eventually. So I have the A-B card that I get from the A and the B, and then I have one more card left. So then I just started working out what this would be. So when I put A and B together, I get AB plus A plus B. And then I have the C card. Okay, so now I do that again. What am I going to do? I'm going to multiply this whole thing by the C, and then I'm going to add both of them together. So I'm going to get ABC plus AC plus BC plus AB plus A plus B plus C. So I have my XY and my X plus Y. Okay, so I did this again 2 more times. And I probably didn't have to do it 2 more times, but I did because what I noticed is that I'm going to get at the end A plus ABC plus AC plus AB plus BC plus A plus B plus C. And in some way there's nothing else that can come out, right? Because I have the triple and all of the pairs and then all of the singletons. So there's nothing else that could happen. Right? So, if I have just 3, I have to get the same output when I come all the way to the end. So then, I was in the process of convincing my group that since we can do this with 3 cards, it really shouldn't matter how many we have. Because, again, all I needed was that A was less than B was less than C. But that they were different numbers. Actually, they don't even have to be different, right? They just have the 3 numbers. So.
All right.
All right, so I think there's a really important thing here, which is at first you think you have 3 things to check. I need to compute all 3 of these things and make sure I get the same answer. But then you realize, actually, if I just checked any 2 of these things, it would be okay, because after all, this one and this one and this one, well, like here, if I just switched A and B with each other, it would turn this one into this one. So if this is the same as this, then it's also going to for sure be. But wait a minute. This is the same as this. I just have to switch the A and the C with each other. Here the B is grouped with the A first. Here the B is grouped with the C first. So if I switch A and C, these will be the same thing. So if I take this big expression and I look at what happens, as soon as I do one of these 3 computations, I'm already done. I have ABC plus AC plus BC plus AB plus A plus B plus C. That came out of this one. If I want to know what's going to come out of this one, I think, well, what happens if I switch the A and the C with each other? Whatever happens here has to be the same as what happens here. If I switch the A and the C, it's going to be the same as grouping it that way. So I come over here and I switch the A and the C. Well, nothing happens here. Nothing happens here. Uh-oh, this one gets messed up when I switch the A and the C. Oh, but luckily these 2 just switch places with each other. And when I switch the A and the C, these 2 just switch places with each other. So when I switch the A and the C with each other, this is unchanged, this is unchanged. Here I just change the order, who cares? Here I just change the order of addition, who cares? I get the same thing. So this is a pretty powerful use of symmetry. And oftentimes people think of symmetry as something that really comes from geometry, like a shape that looks the same when you rotate it or flip it over or whatever. But here's an algebra symmetry, and instead of flipping over the shape, I'm flipping the variables A and C with each other. And instead of the isosceles triangle looking the same when I flip it over, the computation looks the same when I flip it over. Right? So it's a kind of symmetry in algebra. And what this shows is that, well, this property for our operation is pretty obvious. This property is not very obvious, but we've now shown that this property is true. And then just like in all the stuff I erased, if we had any big pile of variables, if we just patiently use these two facts over and over and over and over and over again, eventually we can rearrange any list with any set of parentheses into any other list. And maybe to avoid confusing notation, because that looks a little bit like the absolute value of A times B or something, I'm going to suggest A star B, A times B plus A plus B, just so that we have a notation that we can use that doesn't get confused with other things. At least I've never used the star operation for anything else much before. Okay, so this is really cool, because this has transformed our question. We no longer have the question, what is the largest output? And we have the answer to the question, does order matter? No, it doesn't matter. You get the same answer no matter what. So it's not what is the largest output. Our question now is just, what is the output? There's only one possibility. Just like in the x plus y machine, we know we're just going to get the total. It doesn't matter what order we do the steps in. We're going to get the same total. We've now established the same thing is true about our star machine, just like with the plus machine. Starring all the numbers together is going to give us the same final result no matter what. And so we just need to find out what that crazy number is. Or maybe whether it's odd or even. Does anybody know yet if this final number is going to be odd or even? Odd? How do we know it's going to be odd? But how do we know it's going to be odd?
I'm on the fence.
All right.
It's odd because I said it's odd.
Yeah. Is there a way we can tell? Like, what about the inputs here? If I put in an even and an even, I'm going to get even. If I put in an even and odd, I'll get even, even, odd added up, so that'll make odd. If I get an odd and an odd, odd plus odd plus odd. So the only way it gives two evens out is if it has two evens. The only way it gives an even output is if it has two evens coming in. As soon as I stick an odd number in, anywhere in the process, I get an odd number out. So if I have an odd number at the beginning, I can never get rid of it. I can never get rid of my last odd, because the only way to get even outputs is to put in two evens in the first place. If I have an odd number on my board, eventually I put it into the machine and I get an odd number out, and I still have an odd number on my board, right? And so that's an example of what we could call, kind of goes with monovariance. We could go with invariants, things that don't change. So an example of an invariant is the existence of an odd number. If an odd number exists and I use the machine, an odd number still exists, at least one somewhere, because the output is odd. Or with this machine, an invariant is the total. No matter how many times I use the machine or where in the middle of the process I stop, the total of all the numbers on the table never changes. It's invariant, right? The total being whatever number it is, 5,000 and something, always stays the same no matter how many times I use the machine. At the beginning, the middle, the end, it's always the same total of all the numbers on the table. So looking for invariants, things that don't change when you use your machine or when you go to the next step of the process, when you do your symmetric operation, right? This is another example of an invariant. When I flip A and C, this doesn't change. So looking for the things that when you do something, some things change, but other things don't, can be a really powerful tool as a problem-solving technique too.